is extinction.
Hey, everybody.
Hello.
Hello.
All right. Happy Monday. Okay. So we still have a couple more minutes. I'm going to wait for more people to come in and then I'll get started.
Is that a negation CD or a conditional CD?
Conditional. Okay. So let's get started here. So just a couple things about the homework. I got a lot of emails Friday night at like 9 p.m. about people struggling with the homework and a bunch of people at once. So it's not possible for me to help everyone that soon to the deadline. So it's really important that you guys give the homework a try, especially the more difficult questions before the last class, so that you know what you're struggling with, and I can more specifically target these lessons to help you guys out. Because the derivations are still going to get more difficult than what you've seen on the homework. Not much more difficult. We're getting close to as hard as or complicated as these derivations get, but there's still more room to go for these exercises. All right. So I finished up the other classes. I plan to have all the homeworks graded today. So you guys will get your grades today. Besides that, though, this class, I thought since a lot of people struggled with these questions, it would be useful to go over them and just answer the more difficult ones and show you guys some strategizing that will help you solve even more complicated derivations from here on out. All right, so here we've got one from the homework. Before I start, is there any general questions you guys had about the homework? Any difficulties you had handing it in? Yeah, all good. All right. Okay, so I think this is question 4 on the homework, and I think it's one people had difficulty with. So there was some strategizing I mentioned last week about solving this particular question because I think Judson brought it up, sort of obliquely trying to uh, get at how it's possible to do a derivation like this. And here is one of the confusing parts of this derivation, because we have an atomic well-formed formula that's nowhere in premises. So how do we get that in our conclusion? Might be one question, right? Before, we could just use disjunct introduction to introduce it, right? But it's not attached to a disjunct. It's attached to arrow. Well, the beauty of arrow introduction or conditional introduction is assumptions can sometimes become permanent parts of your derivation, even if you don't find them anywhere before that. So there's a schema just to remind everybody. So it doesn't matter what our assumption is, as long as we get something that's Q, we can make an arrow conditional out of it. And that means in some cases, it's strategic to bring into the derivation a well-formed formula as the antecedent that appears nowhere else in the derivation, as long as you're comfortable with having that condition, the whole conditional be there. Okay. So working backwards here is really important. What's the last rule? Conditional introduction. There's only conditionals in this derivation. So we're only going to be using rules that have to do with conditionals. Right? All the main connectors you see, conditionals in the conclusion and the premises. All right, if we're using conditional introduction to get this, well-formed formula, the first line has to be G assumption. All right, what do we do next? Well, we're trying to get this conditional now. H E arrow IG JG. So IG or G? So JG. Okay. So if we're going to get that conditional, we're going to have to do conditional introduction again. So working backwards, that means a nested assumption rule. And we have to get JG. All right, where can we find JG? Well, some of you might be shouting, it's in the premises. So let us unleash the power of conditional elimination to get us that rule. One, two, and then we're done. All right, my writing is more terrible than usual, but yeah, that's how we do question 4. Any questions about that?
Could you have done an elimination before assuming HG to get JG and then just reiterated that in the sub derivation.
Yeah.
Oh, okay. Thank you.
Yeah, yeah. Yeah. So yes, you can do that. And now you guys can use that reiteration rule. But just be careful because you can't, it's a tempting rule to use to take things out of assumptions when they're already discharged. So yeah.
I got a question.
Yes, Sebi.
All right. So first one, I see why you put BG for an assumption right there.
Mhm.
And then I see why the second one you want to bring in so you could have that HG part of the
Yeah.
equation. But so you pull an HG as your P. And normally, I mean, I know in the back problems, we'd start with like that first one, and then we'd have to find other values through like disjunct elimination or by conditional elimination to craft our own thingy. Um, how come here we're able to just pull out this random value that normally, because before I saw that like we'd put the first value and then we'd able to eliminate the antecedent or the
Mhm.
consequence rather, because we had the antecedent, so we are able to eliminate the consequence. But here we're able just to pull out a random atomic, not a random one, the one we need. But how come in the past problems we had to go through biconditional elimination, disjunct elimination to get that second value of the conditional we need when we
S-
just
so,
have pulled in a random atomic?
uh, so what's that noise? Okay. So Sebi, the answer to your question, I think, is just because we have this new rule, conditional introduction, right? So conditional introduction allows us to introduce things that don't appear in the premises, and same with negation introduction, because they're assumption rules. Uh, and for the most part, strategizing around these assumption rules is such that you're not going to be making too many, bringing too many new things into a derivation unless it's found in the conclusion. But
If we're bringing in new things, how come we can't just go BG as P and then HG just straight up without introducing HG as another P into another assumption?
okay, so you're talking about why can't we just assume the conclusion? Is that what you're thinking? So
Yeah,
just
we have BG written as our P and like that little, where it's introduction, like that whole like formula, the P dot dot
on
dot
line
Q.
two. Yeah, yeah,
We have P as the BG
yeah,
and then Q as the HGJG.
yeah, yeah, yeah. And you're asking, so
Why can't that just go?
can we make the P just the full conclusion?
No, I'm asking keep BG and then just have it as HGJG as a conclusion without anything else.
Um,
Because it seems like if we could pull in random values in atomics, we shouldn't need to go through the HGJG introduction step when we could just go HG to JG right off the bat.
I would just say that, right?
Yeah,
So the reason we can't do that is just uh, simply there's no rule for doing it that way.
okay.
Uh, right. We could have so you're noticing something here that uh, for arrow introduction, there's one kind of arrow introduction. Oh my god. Sorry, my headset just died. Hold on. There we go. Uh, Okay. Can you guys hear me?
Yes.
Okay.
Yeah.
Just give me 1 second here. Okay. So one thing Sebi noticed is that for uh, arrow introduction, there's some cases. Oh my God. There's some cases where it doesn't really make any sense to make an assumption. Why can't we just do something like this? Have some cue, and then uh, like with disjunct introduction, just allow us to say something like this,
Not
right?
not not quite. I wish I could write because that would make it a lot easier. But so I in this equation that in this derivation that we solved, we so go through we keep step 2, BG assumption right there,
Mm-hmm.
right? We ignore step 3 and we ignore step 4 and we just go straight to step 5. Why wouldn't that work? Because we're with the arrow introduction, we're allowed to pull in different values. So why do we have to do step 3 and 4? Why can't we just go to 5?
Uh, so I think I can actually get you to draw, Sebi. So if you go to the bottom, there's an annotate thing.
Uh,
It might be at the top of your screen. It's under view options.
Yeah, or top of
oh,
screen.
annotate.
Yeah.
Yeah, I got that. All right, so now I can. Yeah, oh yeah, I just drew that. All right, so we keep this. This one is good.
Mm-hmm.
I say we keep that, and then what if we ignored this, and we ignored this, and we just straight up assume this? Like this was the last step.
Yeah. So that's sort of what I wrote on number 2 here. Like if that was a rule, what would allow us to write that, right? So one of the most important parts of derivation of doing derivations, or the thing that constrains it to this like very exact puzzle solving activity, is you every single line that you write down has to be licensed by some rule of inference. So if we're going to introduce an arrow, the only thing that can possibly license that is if we have this top part written down before it, right? But if we introduce a new rule, called it arrow introduction number 2, that would allow us to do the thing you're just talking about, right? Because we could just cite which line is it? Actually, we would need JG by itself, but then we could cite that and then just add HGJG, right? The thing that we're missing though is JG by itself. Because anytime you have anything by itself, anything else can be put as an antecedent to it. In the same way that disjuncts can add anything to them. And the reason for that is any line of a derivation is something that's assumed to be true, so long as it's licensed by a rule of inference. If it's assumed to be true, anything that's any conditional with a true antecedent is also assumed to be true. So it doesn't matter what with a true consequent, it doesn't matter what the antecedent is, right? In the same way that if we assume one component of a disjunct is true, we know that the whole disjunction is true. Yeah, so that's how to think of this semantically, what's going on here.
So the only way you could pull in a new value is for that P part, right? Everything
Yeah,
else has to be based off the equation.
yeah. You have to exactly follow the structure, this recipe. So think of arrow introduction, the rule as a recipe. Constraining what licenses the introducing of an arrow to your derivation to this very specific schema, right? Of having something written down as an assumption and then getting at some other line where you discharge the assumption a Q part.
All right. I think that so assumption lines are the only like the actual A lines are the only times you could bring in a value that is out of nowhere. Everything else has to you have to use that line to create something else.
Yeah.
All right. That clears up basically everything.
Okay. All right. Oh, sorry. Okay. So do you guys have any other questions about this derivation? Now, okay. So we're going to go on to one of the more, oh, Sebi, can you erase your annotations, or maybe I can?
Yeah, I'll erase them.
Thank you. That's useful to know, though. So if you guys want to annotate or draw things, feel free. Okay. All right. This guy, I think, posed a lot of challenges to people. I think it was question 6 on the homework. Okay. Oh, yeah, and this is just a reminder. If anyone wants to, or one way to get my attention is there's a raise hand button on the participants menu. If you guys raise your hand, I can just address you specifically without you having to talk in front of, the whole Zoom cluster here. Okay. So, all right. I really liked this problem. It's a fun one. And probably fairly difficult for you guys. So here's one confusing part of it. Or maybe not one confusing part, but one thing that should clue you in on the general strategizing is that the conclusion is an atomic expression. So it's just HA. Meanwhile, we have, for the premises, much more complicated expressions. So for most derivations, that would mean you're using mostly elimination rules. For this one, though, it's going to be a combination. All right. Well, one thing that should be jumping out to you when you see this many premises and a very simple conclusion is looking at the more complex elimination rules like disjunct elimination. So write that out. And one really interesting thing is that in other derivation or other logics, disjunct elimination is an assumption rule. So disjunct elimination is basically 2 arrow introductions, and then you have your disjunct. So anytime you're considering a disjunct elimination, now that we have arrow introduction, you should be thinking of how can I arrow introduce these requirements for disjunct elimination. So it's sort of one of these combo rules now that that you should be thinking of closely associated with arrow introduction, because in a lot of languages it is just a bunch of a couple arrow introductions, so it is an assumption rule. But in ours, it's not an assumption rule. You don't have to make assumptions to do a disjunct elimination. Okay. So I'm just going to say right away that this conclusion, working backwards, is disjunct elimination. One of the biggest clues here is that we've got conditional here that leads to our conclusion, and the antecedent is tied up in a disjunct. So that's the pattern you guys should pay attention to for finding out when to use disjunct elimination. Okay, now for our strategizing, we want to think of how we can get these requirements for the disjunct elimination. We've got 1, we've got 2, but now we have to get 3. So we have to get GB arrow R. And that's what we're going to work towards. Once we have that, we're going to be able to use the disjunct elimination to get HA. So let's just write that down. The bottom is one of our goals, because once we have that, we can complete our derivation. Semantically, and looking at premise 3 here, we know that double arrow is basically the same thing as an arrow going both ways, right? So if we can prove that the arrow going one way is a valid step in this derivation, then we've got the rest of our derivation in hand.
Should that be GB to HA?
Oh, yeah. Okay. Wait, what am I doing? There we go. Okay, how do we get this? Well, now we have our secondary goal, which is getting this HA by itself inside the subderivation, right? So one tempting thing here is to, once we get that HA, just say, oh, we've got the conclusion. But it's important to keep in mind this rule that if we've got the conclusion inside the scope of the assumption, it doesn't count as completing the derivation. Okay, so to get HA, we just do some biconditional elimination. And now we've got the parts we need in order to do 1, 2, and 7, the disjunct elimination. All right, so take a look at that. I'm gonna try and get my headset working again. Just give me 1 second. Okay. Can you? I think my microphone's still working, but I can't hear you guys. This is really frustrating. Select speaker.
There we go. Yay. All right, do you guys have any questions about this derivation? No? Did you guys find it easier than question 4? I'm curious about that.
Yes.
I thought
Yes,
it was a lot
Maddie?
easier. I thought
Okay.
it was a lot easier.
Okay. Next up, we're going to do question 9, which for these homeworks, I actually thought might have been easier for you guys than the other ones, but I'm not sure. Yeah, so let's go through it. So this one has just an interesting twist on strategizing that you guys will have to get used to for the more complicated derivations. And that part of strategizing has to do with, oh, wait a second, no. There we go, okay. So I wasn't hearing you guys. Okay, so now I can hear you guys if anyone said anything. So this part of the strategizing has to deal with using these assumption rules to introduce things so that you can eliminate other things. And I'll show you how it works here. So thinking backwards here, we've got atomic Wolfram formula as a conclusion, and that means we have to have an eye towards eliminating Wolfram formulas. We can also, so the next step is finding out where the conclusion is in the premises it's attached to a conditional. So likely the last rule we're going to use is conditional elimination. But just keeping in mind generally that there are some other possibilities like disjunct elimination, right? Here it's not likely. Okay. So in order to accomplish this arrow elimination, we need this antecedent here of that conditional. So how do we get that? Well, we're probably going to get it from arrow introduction. For arrow introduction, you have to assume AB. Then we're trying to get BC. BC is in one of the premises, so all we have to do is cite and we've got it. Okay. Any questions about this derivation? No? Did you guys find it easier than the other ones? Okay, awesome.
Yeah, it was a lot easier.
Yeah. I thought it would be easier, so I'm glad I'm right. All right, but the one unique thing that this derivation introduces is this idea that instead of arrow introduction just being used to introduce the conclusion, we're looking to arrow introduce in order to eliminate something, right? So it's an important part of strategizing for these more complex derivation, where more of your steps are going to involve introducing something for a future elimination. Okay, cool. So now that we've taken care of what I thought was the more difficult half of the homework, did you guys want to bring up anything else? Okay. So if not, let's move ahead with some, we're going to finish off just practicing some negation introduction.
Wait, I actually have one more, if you don't mind.
Yeah. Go for it, Judson.
Can you do number 5 from the graded homework? Because we had to do 4, 5, and 9 of the of 8.1.
Okay, yeah. Aha, yes. So number 5 is very similar to, I'm just gonna write down my, wait a second. Is that the, I'm just gonna use different atomics, I guess. But have the same. This one's sort of fun. Okay. So this one is very similar to number 6 here, in that you're going to be doing disjunct elimination. But this time, you need to make 2 of these. You have to introduce 2 arrows in order to get these requirements, because in this derivation, you only have the disjunct by itself. So another interesting thing, or interesting side note for you guys, is that double arrow introduction in a lot of other languages. In ours, it's, you know, P arrow Q, Q arrow P, and then that lets you double arrow introduce. So those are sort of semantically equivalent, right? Once you have a double arrow, it means that really you've got an arrow going either way. And arrow introduction, or double arrow introduction in a lot of languages is an assumption rule, similar to arrow introduction. Okay. And that's because really, if I need a double arrow, I could just use 2 arrow introduction rules, 2 assumption rules to make that thing. So whenever you see a double arrow, you can consider yourself having this sort of setup. So having all right. And once we have all that written down, we've solved the derivation. So double arrow elimination, 1, 3, and 2.
Is it possible to do that a different way?
Maybe. What do you have in mind?
I did disjunct elimination. I don't know if you remember, but I asked you on Friday. I was like trying to get at this question without you being able to like give it away, and I asked if the R that value could be the same as the P or Q.
Mm-hmm.
So I did. So like for example, so up to number 5 we had the same thing, but then after that, I assumed. So F A to GB. So then on line 6, I assumed GB, but then I cut it off right there, and then I did GB arrow GB, because then that fits the that fits like.
Yeah, you're right. I actually did this wrong. So, yeah, one of these should be. Yeah, you're right. So, this one's gonna be complicated to change. Right. Because if we're doing this according to how, because I use different atomics, but if we're doing this according to the same sort of form that the problem took, one of these is in fact GB disjunct GB. Yeah, thank you, Judson. Yeah, you're absolutely right here. And so if you're doing this sort of thing, you can use the reiteration rule to make, I'm not too picky about it. So if you're making an idempotent well-formed formula, some people are just citing the line that you make the assumption on. So that line acts as both P and Q. Here I'm making it really, both are right technically, making it really explicit that line 6 GB is the antecedent, line 7 GB is the consequent. And then on line 9, you get the disjunct elimination. So yeah, this is like a really, so question 5, I thought was really important for you guys to encounter because it's important sort of strategizing to be comfortable with disjunct elimination, that you can actually extract one part of the disjunct if you have the appropriate resources, right? Disjuncts are super hard to get anything out of, but if you have something like the resources we have here where one part of the disjunct is pointing to the other part in an arrow relation, we can do the sort of thing that we did in this derivation to extract that thing in just 9 steps or 7 steps. Okay, all right. So that is it for the difficult homework questions. We don't have a ton of time left, but I do want to get to just at least one negation introduction. So negation introduction is going to throw a wrench into things insofar as how you guys think about derivations. Because there's going to be some times where figuring out the last rule is way more difficult. Just because with disjunct introduction, elimination introduction, you can add, it allows you to more creatively approach derivations. All right, but here we've got one that's really straightforward. So we've got a derivation where the conclusion is a negation, and it's pretty obvious here right from the get-go that negation introduction is going to be usable. So here we see a contradiction, right? So if you guys remember, contradictions are things in the form of P, Wolfram formulas in the P form of P and not P. So we can spot one of those and we know we've struck gold. We can use this insanely powerful rule, negation introduction. Okay, so let's draw the schema for that. So if we're going to use negation introduction to get this conclusion, the assumption here is going to be the unnegated form of that conclusion. All right, and then next we extract enough of lines 1 and 2 so that we can reconstruct our contradiction. We're gonna run out of space. Okay, now we can make up our contradiction out of lines 3 and 5. All right, I have to say where I got this from. Arrow elimination. So once we have that contradiction, it allows us to discharge our assumption, introducing a negation into our argument. So for you guys to complete the homeworks for this week, it's really important that you guys are comfortable with finding contradictions and being able to tell what assumptions you're trying to make when using a negation introduction rule. So here, for instance, the assumption is always going to be everything to the right of the negation. Does anybody have any questions about this this derivation? No? Okay. So we're getting close to the end of our session time today. So there was a lot of people worried about the homeworks too and worried about their grades. I'd say, don't worry. The homeworks aren't going to be graded exactly the same as the quizzes. So I know saying that is going to make people more worried, but I'm not out to try and grade them really harshly. That's what I'm trying to say, right? We're all going through like a dramatic shift in our abilities to work and just our habits and lives. So even me, like, I mean, you know, I'm having a hard time getting the same amount of work done that I used to be able to do just sitting inside my house. I'm sure a lot of you guys are finding it the same thing, right? That for me, going to the library and going to the coffee shop was a really important part of my routine for getting work done. Now I can't do that. And so I just sit here and my Nintendo Switch stares at me and it's too much. Or yeah, just being in your house. I've never done.
Oh, stupid headset. All right. So that's all just to say, take it easy. Try and try the problems before the class time, so you guys can come to me for help. So that everyone can, because if you're having a problem, it's likely a lot of other people are also having a problem in the class or struggling with something. All right. If there's no other questions you guys have, I'll see you on Wednesday. Bye.
Bye.